I'm Sri Chantala, Product Manager here at Snowflake, working on Snowpark.
Hi, everyone. I'm Maxim Lukyanov, working at Snowflake on machine learning and data science. In data science community, it is infrequent to hear about difficulties building the model. After all, we have so many tools and frameworks to help us with that. The discussion here usually revolves about how we can build even better models than we were able to before. But what we hear frequently is about the fact that data scientists still spend majority of their time finding and preparing the data that they need for their data science projects to succeed. Finding and getting access to this obscure SQL database in a remote department of an organization can be incredibly frustrating. Data silos is a #1 obstacle on the path of data science team. And when the data is found and the model is built, it needs to be deployed into the same data infrastructure. Disjointed data infrastructures create enormous barriers to machine learning deployment workflows. Each ultimately limits ability of organization to scale their ML efforts. Snowflake offers great solution to data silos problem. Organizations which adopted Snowflake enjoy uniform and secure access to their data assets. Data scientist teams can seamlessly access data across departments in their organization using secure data shares, and can go even beyond boundaries of their organization by getting access to external data sets through Snowflake Data Marketplace. The single data platform that Snowflake offers enables collaboration between teams and simplifies machine learning deployment workflows. There are hundreds of data science teams enjoying the benefits of Snowflake Data Platform. Here's a few examples. Chipotle datasets available on Snowflake Data Marketplace to improve performance of their machine learning models. Count, an Equifax company, optimized their data preparation pipeline and sped up their machine learning workflow, which powers prevention of fraud for over 9,000 businesses worldwide. And Instacart moved their scoring architecture to Snowflake, which dramatically improved performance of their prediction pipeline, which powers more than 200 million grocery item availability predictions every hour. With all of these successes, we are especially excited to announce that now data scientists can do even more directly in Snowflake, and now with the programming language of choice of data scientists, Python. To help me introduce Snowpark for Python, let me invite Sri back to stage.
Thank you, Maxime. Before we jump into Snowpark for Python, let's do a quick recap of what Snowpark is. As Snowflake grew the data cloud, we naturally needed to expand the ways users interact with the system beyond SQL. We thought deeply about how to maintain the simplicity and power of Snowflake for data warehousing while building extensibility into Engine for broader data programmability. And we also thought about the right libraries to enable deep streamlined language integration, allowing more people to work natively with Snowflake to accomplish their tasks. With these goals in mind, last year we launched Snowpark. Snowpark is a new developer framework for Snowflake. It allows data engineers, data scientists, and data developers to code in their familiar way with their language of choice and execute data pipelines, machine learning workflows, and data apps faster and more securely in a single platform. Snowpark's client-side APIs bring deeply integrated data frame-style programming to the languages developers like to use. The APIs are designed to make building complex pipelines a breeze and allow developers to interact with Snowflake directly without having to move data. And on the server side, we have support for various language runtimes that allow pushdown of custom code as functions, which run in a secure sandboxed environment hosted right inside the Snowflake engine. Snowpark currently has support for Scala API on the client side and support for Java, JavaScript, and external functions on the server side. And today, we are very excited to introduce support for Python. The addition of Python to the Snowpark family of languages comes with a wide variety of benefits. First, as a Python developer, you'll be able to work on familiar syntax and constructs with the Snowpark Data Frame API that efficiently distributes computation using Snowflake's elastic performance engine, so you're never bound to the scale of a single node. Second, one of the benefits of Python is its rich ecosystem of open source packages and libraries. To make that easily accessible in Snowflake, we pre-installed the most popular packages from the ANACONDA repository, and we've also integrated the Conda package manager so that you don't have to worry about doing any manual installs or have to deal with broken Python environments because of missing dependencies. And finally, and most importantly, All of your custom Python code gets pushed down to Snowflake to run seamlessly in a highly secure sandboxed environment built right into the Snowflake processing engine. Let us show you all these benefits through the lens of a machine learning workflow. To illustrate the various concepts and benefits of Snowpark for Python, throughout the presentation, we will be showcasing a series of demos structured around building a fraud detection solution. In the demo scenarios, we have Style Me Up, a rapidly growing e-commerce channel who has been experiencing transaction fraud, and they would like to implement a fraud detection solution to reduce costs. We'll see how their data engineering and data science teams can implement the various tasks involved in a typical ML pipeline, such as doing data preparation, building and deploying the model, and automating the pipeline, all using familiar programming concepts and APIs, and a rich ecosystem of open source packages available within Snowflake. Let's start with exploring the data frame APIs.
Data frame APIs is what allows you to compose your Snowflake queries in your Python program using data frame operations. The Python program can be anything. It can be a script that you run periodically, or it can be an IDE of choice like PyCharm or Visual Studio Code. It can also be an interactive notebook environment like Jupyter. Snowpark uses familiar data frame APIs semantically compatible with PySpark. If you're familiar with it, you will feel at home with Snowpark. Snowpark Query Translator supports full pushdown of the data frame queries expressed in the data frame operations to underlying SQL Snowflake. This ensures that you always have native Snowflake performance and scale when you work with Snowpark. With Snowpark, you can easily work with terabytes of data and with billions of rows directly in your Python program. Let's take a look how data frame APIs look like. We'll use data frame APIs in the initial data engineering tasks of our end-to-end machine learning workflow demo. We'll run our demo in Jupyter Notebook. So first, let's see what data sets our online retailer Style Me Up has available to solve their fraud detection problem. In Snowpark, the first step is to connect to Snowflake by creation of the session object. Let's take a look at the orders table. Here you can see how we use a session object to create data frame that represents orders table and retrieve its first rows and display in pandas format using built-in pandas support. In the orders table, we can see a transaction ID, the IP address from which this order originated from, and the delivery address, among other details. We also have orders detailed table which is a simple table that contains details of the items that were purchased in each order. Now with these two tables, our goal for the data enrichment task is to enrich this data set with 3 additional features. Let's start with adding average price per item feature. We'll calculate this feature using orders detailed tables. And below this Snowpark data frame query illustrates how you can do it in Snowpark. We'll join orders and orders detailed table using join operation. We'll group by transaction ID and simply calculate average of the price and save it as an average price per item column. Let's take a look under the hood how this query expressed in Python was translated and executed on the Snowflake. To do that, let's take a look at the query history. Here is our query that we just executed. In query profile, we can see that operations that we expressed in data frame operations were pushed down into Snowflake. We can see that our join operation joins orders and orders detail table, and aggregate operation performs the average that we requested. In the query view, you can also see the full SQL that was generated for our data frame query operations. While we expressed our query in data frame Python operations, we were still able to take full advantage of Snowflake Elastic Query Engine. You can see that our query processed 1 million of rows in about 4 seconds, while without any movement of the data from Snowflake. Let's move to the next stage of our demo. For the next 2 enrichment operations, we'll take advantage of the external data sets available on the Snowflake Data Marketplace. We have acquired 2 data sets from IP Info Company. The first data set, IP address privacy detection, allows us to determine for each IP address whether it was masked behind VPN, proxy, or Tor network. We have a hypothesis that adding this signal into our machine learning model will improve its prediction power. Similarly, we'll use geolocation dataset, also from IPinfo company, to map IP addresses and zip codes into their geographical coordinates. First, let's join information from our privacy dataset. This is a fairly complex join, which requires us to do join in basically 2 steps. The first step is an approximate but fast join that uses 2 join key to reduce the number of rows that needs to be considered for the join. And second step of the join is where we perform a range lookup to locate exact rows that corresponds to our IP address in the privacy dataset. One interesting fact here is that the 2 join key operation is provided to us by IPinfo company. It's provided as a custom SQL operator, and Snowpark allows me to use that and integrate into my query by using this built-in methods. Now we have acquired and enriched our dataset with isMasked properties that represents whether a given IP address was masked or not. Our last enrichment operation is the most complex. To simplify my code, I actually created a helper function for me to perform it. While this operates, let's take a look at this function. In the interest of time, we will not get into details of the function, but it's a good illustration how we can express a fairly complex logic in a composition or in the sequence of the simpler operations on the data frames. I can also package this logic into a reusable function so I can use it later. Now we have enriched our dataset with 2 locations. One is for location of the IP address, and second for the location of the delivery destination. Before we jump into the next segment of our demo, let's talk how we can do more advanced data engineering operations using Python functions.
We just saw how with Snowpark, you can conveniently write data frame operations that are converted into SQL queries that run right inside the Snowflake engine. But Snowpark is a lot more than just a nice way to write queries. You can bring along your custom Python logic as well by declaring that the function is a user-defined function and then make use of it in your data frame operations. Snowpark then takes care of serializing the custom code into Python bytecode and then pushes down all of your logic to Snowflake so it runs right next to your data. To host that code, we've built a secure sandbox Python runtime right into the Snowflake engine. And finally, with Snowpark, you have seamless access to hundreds of curated open source Python packages made available directly in Snowflake from the ANACONDA secure repository. If you think about it, the power of Python lies in its rich ecosystem of open source packages. And in the recent years, open source packages have been the biggest enablers of data science. As part of the Snowpark Python offering, we wanted to bring enterprise-grade open source innovation to the data cloud while helping ensure a seamless experience for data scientists and developers to do their work. And this is made possible as part of our recent ANACONDA partnership and product integrations. Snowflake Data Cloud users who already benefit from instant and governed access to data will now be able to speed up their Python-based workflows by taking advantage of the seamless dependency management and comprehensive set of curated open source Python packages provided by ANACONDA. Let's take a closer look at how Snowflake and ANACONDA will enable innovation. As I mentioned earlier, a curated set of open source libraries built and published by ANACONDA are pre-built into the Snowflake environment. For convenience and purposes of local development, the same set of libraries and versions are also made available on a Snowflake channel hosted on the ANACONDA repository. When developing locally, you can simply point your local Conda installation to the Snowflake channel, which will ensure you're using the same packages and versions available on the server side. So if your function depends on any third-party libraries, during UDF declaration, you simply specify which Python packages the function needs, and Snowpark automatically picks up and resolves the dependencies on the server side and installs the relevant packages into the UDF environment. The dependency management is made seamless by the Conda package manager, which is transparently integrated into the Python UDF creation workflow. This is immensely valuable as without the right toolset, resolving dependencies between different packages can land developers in a dependency hell, which can be a huge time sink. Compared to existing solutions and systems that use pip, the Snowflake ANACONDA integration will enable users to effortlessly process their data with the latest open source innovation without having to worry about conflicting dependencies. This means developers and data scientists can spend more time innovating rather than debugging broken Python environments. All of this is made available to the Data Cloud users at no additional charge beyond the standard warehousing costs. And finally, when the UDF is executed, it is distributed across the Snowflake nodes and benefits from the scale and secure processing provided by the Snowflake processing engine. To see this in action, let's go back to our demo scenario. Now that we have the enriched data set that has the geocoordinates of the order and shipping locations, I can write a simple Python UDF that makes use of open source geospatial libraries to engineer a new feature that will give us the distance between the two locations. Going back to our demo notebook, here I wrote a simple Python function that calculates the distance between 2 points using the GeoPandas library. Snowflake's new support for Python user-defined functions is an easy way to turn ordinary Python functions into something scalable. There are many ways to register a function as a UDF. Here, I use the UDF decorator, which lets Snowpark know to push down my Python function into Snowflake as a UDF. The add packages method lets me specify any third-party dependencies my code depends on. The function itself is very basic. It takes in 2 sets of coordinates, and using the helper functions from the GeoPandas library, it calculates and returns the distance. When I execute the cell, under the hood, Snowpark registers my function as a UDF on the Snowflake backend. And as part of the function creation flow, the integrated Conda solver automatically solves for the GeoPandas libraries and its required dependencies and loads the needed packages into the UDF environment. Now that my function is created, I can use it as part of other data frame operations. Here, I call the UDF on a previously enriched data frame, and it returns our new IP to shipping distance feature. If I go to the Snowflake backend, I can see on my behalf, Snowflake created a temporary stage and packed and uploaded my Python code as a zip file to that stage. Here, I can see the temporary Python UDF that was created, which imports my code from that stage. And finally, this query shows the SQL that was generated when we called our calculate distance UDF. This shows that all our custom Python code got pushed down to Snowflake and ran seamlessly in a highly secure sandboxed environment built right into the Snowflake processing engine. Now, as a final step, I find the original data set with the newly created features and write the results to a new Snowflake table. Maxime and his team can now use this enriched data to test our hypothesis and build an ML model. You saw how we can use simple Python functions and libraries to calculate distances. Now, let's see how we can also use Python objects with our functions.
Thank you, Shri. One of the advantages of Python as a programming language is its extreme flexibility and buttery-smooth syntax. This is especially true for Python functions. As a developer, you can pass function around as an object, and Python will make sure that this object has everything it needs to function correctly. This functional principle is what Snowpark fully implements and extends to Snowflake. Snowpark Object Serializer detects when your function that you register in the Snowflake uses objects in their environment and automatically packages these objects together with the function definition. This ensures that this function in Snowflake environment operates exactly as expected. All kinds of stateful Python functions are supported. For example, anonymous Lambda functions with local state, or function defined in a notebook, which happen to use other variables from the notebook environment. Let's see how this looks in action. In the next segment of our demo, we'll train machine learning model and then deploy and inference it in Snowflake using Python functions. I'll start by taking a sample of our new enriched dataset to visualize it in the notebook and start building an intuition about the new features that we have developed. First, I will build a Venn diagram that represents the relationship between fraudulent transactions and masked IP addresses. There is clearly a large overlap between the two, which makes it a promising signal to use in my machine learning model. For the distance feature, I'll plot the IP address locations on the map. The size of the bubble here corresponds to the distance to a delivery address, and the yellow color represents fraudulent transactions. We can see a significant number of large yellow bubbles here, which indicates correlation between distance and fraudulent transactions. So far, our new features look promising. Let's go ahead and train fraud prediction model using scikit-learn and XGBoost. Resulting model accuracy is fairly high at 90%. When I build a feature importance chart, we can see that our 3 engineered features are at the top of the importance for our model. Specifically, mask type P feature that we acquired from the Snowflake data marketplace revealed itself as a top contributor to the model predictive power. Now, with these results, let's deploy this model to Snowflake to run predictions at scale on new transactions. To do this, I'll deploy my detect fraud function to Snowflake. As we have seen with Shree's demo, it's incredibly easy to do with Snowpark. I add the decorator to my function and specify which packages it needs. Snowpark also detects that my function, in order to make predictions, uses model objects that we just trained in the notebook. So it packages this object together with the function definition and deploys it to Snowflake. In addition to that, I also deploy this function as permanent function, so we can use it in subsequent stages of the demo, even after my current Snowpark session is complete. And stage location indicates where the artifacts of the function will be stored. Now that I have this function deployed into Snowflake, I can run predictions on the new transactions table. It has approximately 1 million rows, but in a few seconds, Snowflake completes the inference. Now we can see predictions for new transactions are being generated. Let's take a look at the query, how this function was pushed down into Snowflake. In a query profile, we can see that our function detect fraud was executed as an extension function as part of the query. It is fairly computationally expensive and used 87% of all compute used for this query. Yet Snowflake elastic processing engine was able to efficiently scale this function across multiple nodes and executed inference of the model on 1 million rows in under 10 seconds. If you look at SQL query, we can see how our function was used directly in the generated SQL query. This opens multiple scenarios of where we can use Python functions in SQL. Let's take a look at other scenarios of how we can use Python functions in SQL in more details.
As you saw so far, the Snowpark API has the ability to push both data frame queries and custom logic into Snowflake, where it can run right next to your data. But why let developers have all the fun? SQL is still Snowflake's bread and butter, so we made sure that SQL users can get the full benefit of Python functions as well. With Python functions, developers can build complex logic that exposes a simple function interface. To build these functions, when you have something basic to do like calculating the distance between 2 points, you can write the code as simple inline definitions directly in the Snowflake worksheets. But for more complex use cases, developers can make full use of their existing tool sets, such as their preferred source control integration, their preferred development environments and debugging tools, and they can develop and test the code locally and then bring that code to Snowflake. They can also bring along third-party libraries. Find some useful code on GitHub, use it in Snowflake. To get it into Snowflake and use it with SQL, all you need to do is package the code as zip files and load it into a Snowflake stage, and then specify it as imports when registering it as a Python user-defined function. We think this is pretty easy and lets developers use their existing tooling, which is great for complex use cases. And with this in hand, once you create your Python UDF, any SQL user can use this logic you've just built like any other function as part of regular queries. Since Python functions are usable nearly anywhere functions are used, this then allows you to automate ELT, ML, and CI/CD workflows using streams and tasks. As a final part of our demo, let's see how we can automate scoring of new incoming transactions using the detect fraud UDF that Maxime has created by using tasks and streams. There are multiple options to bring data into Snowflake in a streaming fashion. One option is to use Snowflake's native periodic data loading capabilities with Snowpipe. Then, as new transactions come in, the goal is to score them using our detect fraud function by leveraging Snowflake's streams and tasks functionality. I've already created my Snowpipe and also created 2 new tables that are needed. The first raw transactions table I created is to hold the newly arrived transactions loaded from Snowpipe, and the second scored transactions table is to hold the processed and scored transactions. Here is the simple code you can use to create an append-only stream object that captures newly inserted rows, which fits nicely for processing newly ingested rows, which is exactly what we want. Logically, you can think of the stream object as a table, but a table that contains only records that are new since the last time any data was selected from it. Once a DML query is made sourcing the stream, the rows returned are considered consumed and the stream becomes empty. This is similar to a queue in programming terms. Now that we have our stream in place, we can create a task. You can think of a task as a step or series of cascading steps that can construct to perform ELT operations. Tasks can be scheduled similar to cron jobs and set to run by days, times, or periodic intervals. The following simple task will score the incoming transactions using the detect fraud UDF and insert the scored data into a new scored transactions table. It will check to see if new record exists in the stream every 5 minutes. If records are found, the task will run. The scheduling can be customized to run as needed. We now have our automation in place to score new incoming transactions, and this concludes the final demo for today's session. Before we wrap up, let's do a quick recap of everything we saw so far. Using Snowpark for Python, we were able to accomplish various data engineering and data science tasks to enrich data, build and deploy a machine learning model, and automate predictions. Using the data frame API, we were able to write efficient queries to collect and enrich our original data set. Using Python functions and third-party libraries provided by the ANACONDA integration, we were able to create and deploy UDFs for advanced feature engineering and ML scoring natively into Snowflake. And finally, we were able to automate predictions on new incoming transactions by calling our detect fraud Python function directly from streams and tasks. Using Snowpark for Python, we were able to achieve all of this by using familiar tools and programming languages while still benefiting from the scale, security, and performance of the Snowflake engine. As you can see, we did not have to move any data out of Snowflake or spin up any additional systems. Hope you've enjoyed this session, and thank you for joining.